How's it going, ladies and gentlemen? This afternoon, I'm going to do things a little bit differently. We're not going to be focusing on the book as much as we were in previous lessons. We are currently on topic 9, lesson 2, and that starts on page 440, I believe. Yep, page 440. Okay, so you can follow along in the book with what I'm doing. Okay, take notes. We are going to be looking at some computer models of movements of objects in space, and I'm going to be doing some demonstrations to kind of show you how this stuff works. It's not something you can easily explain just reading a book, looking at paper. Sometimes diagrams can be confusing. So I like to make this as movement based as I can, because I'm describing movement to you. So I think I would need to use movement in order to show you that. All right, so here we go. So the first thing that we talk about on the next page in the book is axis and rotation. Okay, I am on an office chair. Okay, and the office chair allows me to swivel like so. Okay, this is an example of rotation. Quiet, Alexis. I don't know why I just called her Alexis. Alexa. Now she's going to turn on again. Okay. Sorry, just got in a fight with Alexa. 1 second here. Okay, I'm back. Alright, so, axis and rotation. Okay, there is an axis of rotation on this chair. Okay, there's the pedestal in the center, which the chair sits on. And that is what allows me to rotate. So I'm rotating on that axis. Okay, so I'm not moving around the room, I am spinning. Okay, spinning is a good way of describing what rotation is. Okay, if I apply that to something more like a planet, my globe is still in the building, and I can't get in the building and to get in my classroom to get the globe. So here's a kid's ball. Okay, now if we're talking about axis of rotation, now I just put some tape on here, and I'll tell you why for later reasons, but if we're talking about axis of rotation, if we're considering this a planet like the Earth, okay, it's going to spin on its axis. And I'll explain why I'm not holding it straight up and down, right, in a minute. But it will spin on its axis. And this is what controls daytime versus nighttime. Now, if this little blue dot on here represents where you are, okay, we can look at it like this. All right, so currently, sun rises. We see the sun. It's a beautiful day. And then the sun sets. Now it's nighttime. Go to sleep. Alarm goes off in the morning. Time to wake up. Sun rises. We're past noon now. Dinner time. And sun sets, and we're back to sleep. Okay? That rotation is what causes the days on our planet. Okay? So if I'm the planet, and let's say you're the sun, okay, I'm facing you right now, so it's daytime, nighttime, daytime, nighttime, daytime. Okay, so night and day is controlled by the rotation or the spinning, okay, of the planet in space. Either that area is facing towards the sun or facing away from the sun. Towards the sun, away from the sun. The next point I want to make is about revolutions or orbits and how this is different than rotation. Okay, so as we said, rotation is a spin. Okay, a revolution is an orbit. So if this is still the Earth and the red ball now represents, let's say, the moon orbits around the Earth. Okay, so it's not a spin, but an object moving around another object. And generally, the object with less is going to orbit around or revolve around the object with a greater mass, right? So our planet having a greater mass than the moon. Now, don't be confused with mass and size because they don't always go hand in hand. All right, so remember, something that is really dense can have a smaller volume but have more mass. So if this squishy rubber ball, okay, was this big, and this red ball, let's say, was made out of steel, and I just painted it red, okay, this ball is going to have a lot greater mass than this one, okay? So don't let size always confuse you. Now, generally, if everything's made out of the same substance, as something increases in size, it's probably going to also increase in mass, okay? So if these were both made out of the same substance, I could probably infer that this is more massive than this one. But unless I know that, I can't make that inference. Okay, I can't make that hypothetical estimate, right? So knowing what the things are made out of helps you determine relations in mass, right? Especially when it comes to things like planets and moons that we can't exactly easily take measurements using the tools that we would in a lab room, right? For instance, there's a lot more to it than that. Right, so rotate, so rotation, revolution. Okay, revolution, rotation. All right, so the next point we're going to talk about is how the Earth has and rotates through all of its seasons. Okay, now in order to do this, normally in the room I would have a globe and I have a really strong light that I would use. So here's my globe. Okay, bring it out again. This dot's just going to represent right where we live. Okay, Buffalo, New York, northern hemisphere, southern hemisphere, equator. Okay, so in the previous lesson we talked about different zones on the planet. Okay, we talked about the polar zones, right near the North Pole and South Pole. We talked about the temporal zones, which kind of band somewhere in the middle here between. So we had tropical, temporal, polar. Right, tropical, temporal, polar. Okay, now reason going back to why when I was showing you rotation, I had it tilted. Okay, the axis of rotation of our planet is not straight up and down. Okay, it doesn't spin through space like this. Right, so the Earth is going to revolve around the sun. Okay, sorry, there's no easy way for me to do this. So if this is the sun, be going like this. Okay, now the sun's a lot bigger than the Earth, so this is not the scale. Okay, but it's not straight up and down. It's got a tilt to it. Okay, so as this is going around, right, different parts of the Earth are going to be more pointed towards and more pointed away from the sun at different times of the year. Okay, once around, one revolution is a year. So if I start here and go around, that's 1 year. Okay, and as that's doing it the whole time, it's also revolving. It's also spinning. So as it travels around, it's going to have nights and days. Okay, every time it's facing towards the sun, daytime, facing away, nighttime. As it goes around. Okay, now I don't have my super bright light, so knowing me, I'm going to use a lightsaber. Okay, now if I turn it on, and it's really bright, so I'm going to hold it back a little bit. Now we can see in this scenario which part of the planet is more lit up, the northern hemisphere or the southern hemisphere. All right, so the part above the blue tape or the part below the blue tape. Okay, so there's definitely more lit up above the blue tape than below the blue tape. Okay, so in this scenario, the northern hemisphere, right, the part we're in, is going to be experiencing summer. Okay, and then This will rotate around to the sun. Now it's going to be on the other side of the sun. Okay. We'll put us in daytime. Sorry about that. That's bright. Okay. So now, let me get this angled right so you can see it. Now if you look, now that's on the other side of the sun, more of the southern hemisphere, the portion below the tape, is lit up, and there's less light lighting up the northern hemisphere. This, for us, right, in the northern hemisphere, would be winter. Okay, the winter time would be when the Earth is over here and the sun's over here, and then when they rotate around, and the Earth revolves, I used that word incorrectly, sorry, revolves around to the other side, right? This axis always points in the same direction. So whether it was on this side of the sun, okay, or this side of the sun, the North Pole and the South Pole are always facing the same points in space. Okay, so this causes different areas of the planet to receive more direct sunlight. Okay, and that's what causes them to be warmer during the summer, and for instance, for us, if we were pointed like this, colder during the winter. Now, what do I mean by direct and indirect sunlight? Okay, so if I'm looking at this scenario, the sunlight's coming this way. So in the northern hemisphere, we're experiencing summertime. Okay, if we look here, the equator on both examples was always lit up. Okay, the equator and the tropical region are always going to be getting the most direct sunlight. And what I mean by that is the sun rays are hitting those areas at a 90-degree angle. So if I measure the angle, right, against the surface here, that's almost straight up and down. Sunlight's hitting it, complete right angle, right, perpendicularly, right, perpendicular strike. Now, as I move up, right, it's not quite perpendicular, but it's still, it's close. But if I start going down here, notice that angle changes drastically, right? Here, boom, right angle. Down here, not so much. This is an example of indirect light. All right, so the light is kind of like glancing off the surface and traveling around it. Okay, so it's not a direct perpendicular strike. Okay, where you're going to see, for instance, more all year long in the tropical regions. Right, so whether it's tilted like this or tilted like this, there's going to be more direct sunlight hitting this area, which is why this area of the planet, all the way around, okay, is generally hotter than if you travel more north or if you travel more south. Okay? Now, the direct sunlight is going to be responsible for our summers. Indirect light is going to be responsible for winters. So while we are receiving our summer in the northern hemisphere, they are receiving their winter in the southern hemisphere. Okay, if I change that. All right, there we go. So much easier with a globe. All right. So now, if I change it so we are, here we go. More like this. Okay. Now, more direct sunlight is hitting the southern hemisphere. See how much more is going to be directly lit up by those rays of sun. Okay. Once again, this is always getting hit constantly with a pretty good amount of direct sunlight. That's why it's warmer here. Okay. But a lot of direct sunlight, boom, right here. So now the southern hemisphere is experiencing their summer, while the northern hemisphere is getting more of that glancing, right? Glancing blows of light here. They're not directly perpendicular hits. Okay? So while the southern hemisphere is experiencing its summer, the northern hemisphere will be experiencing its winter. Okay? So where does spring and fall come in? Well, as this rotates around, now you notice if you're the sun, Boom, you're shining straight on here now. Whole thing's lit up pretty evenly, huh? Okay, if I flip it around the other way, it would be the same thing. Okay, both the north and the south are receiving equal amounts of light, right? That's going to take care of things like spring and fall or autumn, okay? So as the earth revolves around the sun, our seasons change. So this is the blue dot is us, okay? Light's coming this way. There's our winter time. As it moves this way, here's our springtime. As it moves this way, okay, there is our summer. Keeps going. Fall. And then we're back to winter. So I'm like going this way. Okay? Okay, so now I'm going to bring your attention to page 443, if I can. Here we go. All right, so if we look here, this is just a diagram of everything I was just talking about, okay? So if we're looking here, we have the Earth's orbit, all right? This is how it revolves around the sun, okay? And then we see how the sunlight is shining on the Earth. Now, just keep in mind that you are not looking at this diagram as an above view, okay? So you're not looking down on this diagram, you're kind of looking at it at an angle, like kind of from the side. So really, this is not an oval, okay? This is going to be extremely close to circular, okay? There are times at which the Earth is slightly further or slightly closer away to the sun, but if memory serves me right, it's actually its furthest point during the Northern Hemisphere summer, I believe. I could be mistaken, but it's so slight in terms of travel in space that it doesn't really make a difference. So the distance that the Earth is from the sun makes no difference when it comes to our seasons. Okay, that does not control the seasons. That is a misconception. Okay, we are not closer to the sun in the summer and further away from the sun in the winter. We are receiving more direct sunlight in the northern hemisphere during our summer in June, right? And we're receiving less direct sunlight, right, during our winter in December. Okay, equal amounts in March, right, during our spring, and equal amounts in the north and the southern hemisphere during the fall. Okay, so and remember, as it is revolving, as the Earth orbits around the sun, it is also rotating on its axis, right? Which I already said before, always points in the same direction. So if I'm over here, right, notice the South Pole is here, North Pole is here. Keep going, still pointing in the same direction. North, South, North, South, North, South. So these opposites here, right? Summer, winter. These are known as the solstices, right? A solstice is the point where it's either the area in which you live is either receiving the majority, the most direct sunlight it will receive in the year, or where it's receiving the least amount of direct sunlight that it will receive in the year. Those are solstices. So we have the summer solstice for the northern hemisphere over here, and we have the winter solstice for the northern hemisphere over here. Now remember, if you live in the southern hemisphere, if I'm in Australia, or if I'm in Brazil or Chile, it's going to be opposite, right? So if I'm in the southern hemisphere, if I'm down here, okay? So if I'm down here now, okay, over here, right, I'm actually going to draw this out here. All right, so there's my equator. So if I'm in the north, then right here would be, so if in the north right here, this, I wish my pen would write, would be summer solstice, and over here would be winter solstice. Over here in the south would be summer solstice, and over here would be winter solstice. Okay, so they're opposites. When we're looking at, right, March and September, okay, there's still going to be opposites, but those are what we call the equinoxes. So the northern hemisphere and the southern hemisphere are experiencing the same amount of direct and indirect sunlight. Okay, which one it'll be depends on which season it just was. For the northern hemisphere here, it was just winter. So next after winter comes spring. Okay, but for the south, it was summer. So the next thing after summer would be fall equinox. Over here, right in the north, it was just summer. So we're approaching winter. So here's our fall equinox. And if we're in the southern hemisphere, we were just in winter. We're approaching summer. So here's our spring equinox. Okay. Okay, so next up, I want to show you a cool little computer simulation. If you're interested in playing around with these, there's a whole ton of them. You can go to this website right here and click on the Sims simulations, and you can play around with any of these. They're really cool. This one right now is focusing on gravity and how things orbit. Right, so I'm just going to set up a few things here. So right off the bat, let's just look at the Earth and the Sun. Okay, that's something we're really familiar with here. And so as we're looking here, as it's revolving, okay, or orbiting now, so as the Earth revolves around the Sun, you can see the Earth days pass, right? 365 and a quarter days a year. So boom, we just reached 1 year all the way around, right? When it comes back around again, that'll be year 2, okay? Let's look at a few different things here. All right, so this allows us to track our path. Okay, in this instance, we're looking straight above the orbit. Okay, so we're looking down on it, and as you can see from what I said before, it's basically circular. Okay, very close. If I click here, this is showing the gravity. All right, between the two bodies in space. Right, so we have the sun and we have the earth, and they're going to have a gravitational pull on each other. Now in this instance, the sun has a lot greater of a mass than the earth, so the earth is being kept in an orbit around the sun. Okay, I don't know what just happened. Okay, sorry about that. So the earth is being kept in orbit around the sun. Now, if I click on this velocity button here, this red arrow represents the direction, all right, the direction and speed, all right, which is velocity, speed with direction, the Earth wants to travel in, okay, but it's being kept in this orbit by the gravitational forces between the two bodies, all right? The sun is pulling the Earth into this orbit. So the Earth, if I were able to release the Earth from its gravitational pull, it would travel in the direction of the red arrow. Now, let me see if I can do that. I might be able to do that by making the sun's mass less, which I just did. And you notice it still has some effect on it, but now the sun has lost the Earth. It is not massive enough to keep it in its orbit. Now, I don't know if it's just a looser orbit and eventually it will come back around. I've sat here for a while and watched this thing and it didn't, so I'm assuming it won't. But as you can see, the Earth has just left orbit because now the star's mass is too small in order to keep a planet the size of Earth, right, in its orbit. Okay, so now we're going to do something similar, except this time we're going to use the Earth and the Moon. So I'm setting it up right now, just normal size of everything, the mass of everything is the same. Okay, I set it on fast forward because I don't want to sit here and watch it, so it's moving faster. So you notice here, it's counting the amount of Earth days that it travels. So I'm going to clear this. So if we watch, it takes about a month, all right, for the Moon to revolve or orbit, all right, around the Earth. Okay, so when we go back into talking about moon phases, which we'll be talking about again shortly, we see these phases of the moon occur about approximately, it takes about a month. Okay, so it's going to take approximately a month for the moon to go through all of its different phases and change the way it looks in the sky, right, as it goes through that cycle. Okay, now we're looking here, we still have our forces, all right, so we have the force of the Earth, gravitational force and pull between the Earth and the Moon. We have our velocity, so if all of a sudden the Earth disappeared, that's the direction the Moon would fly through space, just zip right through. Now, this continues to happen because of an important thing, inertia. Okay, if we go back to our forces and motions unit, we remember that inertia is what keeps an object in motion. So this moon will continue to orbit the way it is around the Earth until something is able to stop it or change its direction. Okay? That being said, on Earth, this doesn't happen for an infinite amount of time, right? So even if I was swinging something over my head, okay, it eventually, when I stopped the force behind it, it eventually would stop swinging around, okay? In space, there is no friction, okay? It's a vacuum. There's no outside forces stopping this moon on its present course, unless it collides with something else, okay? That's how things change direction in space. Basically, they get hit by something else, or they run into something else. So if we're looking here, and let's just play around with this a little bit here. Let's see what happens when I make the Earth more massive. All right, so what happened? What happened to our orbit? Okay, our orbit has kind of collapsed in closer to the planet. So now the moon is orbiting much closer to the planet, particularly in certain areas, and that has to do with the timing in which I made the planet more massive. Right? The way this one works is I can't just change the mass and adjust where the moon is, like the moon wouldn't start closer. So it was around here, and then when I adjusted it, that pulled it in closer and created this kind of elliptical orbit where it gets real close and then it gets slingshotted around the planet. So it's actually moving slower over here and kind of faster over here. If you can see that on that velocity bar. So the red arrow is longer when it gets closer and shorter when it's farther away. All right, so the whole force of gravity pulling on these objects is pulling the moon faster through space and increasing its speed. Okay, so it's kind of like slingshotting it around here. So it moves through this area of space faster than it moves through this area of space. If I keep going, try this again. Okay, now the Earth was way too massive and the moon would not stay in orbit, and it actually collided with the planet. And then if this was the formation of a planet early in a solar system, this is how rocky planets and other planets get bigger. They collect debris that's floating through space. It gets too close. Their gravity of the planet pulls that object in, and boom, now it becomes part of that planet. This is also why when we talked about meteors falling through the atmosphere, okay, that they're pulled into the Earth's atmosphere because of the Earth's gravity. The Earth is a much more massive object than the meteor itself, and that's why it gets pulled into the atmosphere and eventually either burns up or collides with the planet. One more thing I want to point out. In the book, it was talking about how gravity works and how the two things that you need in order to determine the strength of gravity is the mass of the objects involved and the distance between them. If we're looking at, for instance, going back to our Earth and Moon scenario here, if I make the planet Earth more massive, you can see right? You can see the arrows that represent the force of gravity, right, of those two objects pulling on each other with a lot stronger of a force. The bigger the arrow, the more the force. If I decrease the mass of the planet, the force weakens. It gets smaller. Okay? Same thing happens with the moon. If I increase the mass of the moon, the force attraction between the two objects increases. If I decrease the mass, it goes down as well. So let's see what happens here. So I'm going to start this scenario again, all right, just like I did. Let's put the path on, okay? And now this time I'm going to play around with the moon. Let's see what happens. Increase the mass of the moon. Increase the mass of the moon. Okay. So the attraction is staying the same. Now I'm not seeing a difference in path. All right, let me start this over. So watch the Earth. Okay, so the path is staying the same, but watch the Earth. There's a slight wobble to it. Right? A slight wobble. Now watch the wobble when I increase the mass of the moon. Now, to me, it looks like the Earth has got a little more wobble to it, because you're having more of a pulling effect from the moon on the Earth than there was before. So these two objects are pulling on each other. It just so happens that the object that has a greater mass is going to kind of win the tug of war, which is why the other object orbits around it. Okay? When the objects are closer in mass, they're going to pull on each other, and it's going to have kind of a wobbling effect. If you notice, the Earth is kind of moving through space now, and you see this path that the Earth is making, this wobble path that we see here. It's not really staying in the same place. And we can see this in, for instance, different stars. Sometimes stars actually orbit around other stars. So you have two stars. I just realized this window's really small. Sometimes you have two stars and they're orbiting around each other, and they kind of play this tug of war, and they have this little wobble kind of feel. And you'll see other maybe planets or other things orbiting kind of around that tug of war. Okay, so they kind of have this little wobbling effect. So solar systems don't necessarily have always just one star. Sometimes they can have more than one, like two, for instance. Alright, so ladies and gentlemen, I think my time is up. This video's gone on long enough. I hope it was informative for you, and I hope it helped. Please go back through the book and read about everything that we were just discussing. And make sure to finish, what page was it? Page 448 is where your lesson 2 check questions are. So please make sure that you type those out and submit them in the comment section below the video. Alright, I hope you guys are having a great week. I hope that everything is going okay. Hope everybody's healthy and happy. And if you have any questions, please do not hesitate to ask. That's what I'm here for. That's my job. All right. Have a great day, guys. Take care. Hope to talk to you soon.